So far, the calculus of functions, we've done single variable up until this point. But in the real world, what we see often depends upon two or more variables. So in this chapter, we look at functions of several variables and head into that. So this section begins with functions of several variables, and we're going to do them from 4 points of view. It'll be verbally, which is description in words. Numerically, we're going to look at a table of values. Algebraically, we're going to have formulas, and visually by graphs or level curves. So we're getting into all of that. So let's start with the function of two variables. So think of temperature at a point on the Earth. Now, this temperature depends upon our longitude and our latitude. We could call our longitude X and our latitude Y. So once we do that, we can think of the temperature as a function of X and Y, or the function of the pair X and Y. So we tend to say the temperature is a function of X comma Y. This is where you get into your multivariable calculus. The volume V of a circular cylinder, if you think about a circular cylinder, the volume V depends upon the radius and the height. So we have the radius and the height. Then the volume equals pi r squared h. So you can see those happening. We can rewrite it to say the volume of r and h equals pi r squared h. And you look at me and say, we've seen that before, but that's true. You've always been given two of the three variables, but in this case, r and h are both variables that can change, not one of them is static and the other one changes. So that's where this difference comes in. So here we have a definition. A function of two variables is a rule that assigns each ordered pair of numbers x, y in a set D a unique real number denoted by f of x, y. So what that says is here we have our x, y graph. We have some point here, x, y, and this is our domain. So compare that to what you know, and it gets mapped to a range. So we're going to call this our z line here, and it gets mapped over here to f of x, y. The set D, so over here we have the set D, and that's everything that we have in here. So down here we could have a comma b, and it gets mapped to f of ab. And then we have some value. Let's put it in green. Let's pick a point here, and it gets mapped over here to this one. So whatever it is, f of mn, and this is m comma n. So you take your domain values and it gets mapped to a range, and this is our z-plane. So the set D, right here, the set D, is the domain of f, and its range is the set of values, and it's defined to be f of xy, such that xy is in the domain. So if you compare that to your notation before, we had f of x equals y, and it's the same thing, we're just moving into multivariables. We often, I'm going to cross this off because we're not living in this world, we often let z equal f of xy, and that lets us know that the third value z is a function where we plug in x and y. In this case, x and y are your independent variables. So x and y are your independent variables. And z is your dependent variable. So if you compare that to what you already know, it makes perfect sense. It's just, you have to think about the fact that over here, our domain is R2, not just a value, and the range is a subset of the real numbers. So for this example, it says for each of the following functions, evaluate f of 3, 2, and find and sketch the domain. So let's start with f of 3, 2. Letter A is the function x comma y, and the numerator is the square root of x plus y plus 1 over x minus 1. So when we plug in f of 3, 2, this means x is 3 and y is 2. And it's just like evaluating a function before. It's just we're in multiple variables now. So 3 plus 2 plus 1 over 3 minus 1. So f of 3, 2 equals 3 plus 2 is 5 plus 1 is the square root of 6 over 2. And let's look at the domain. So this is the first part of the answer. Now for the domain, let's look at the top. You have the square root of x plus y plus 1. So we know that when we have a square root, we have x plus y plus 1 has to be greater than or equal to 0. And in the denominator, we have x minus 1 does not equal 0. So this gives us x cannot be 1. So we put these together to find our domain. We're going to say the domain is the set of all xy such that x plus y plus 1 is greater than or equal to 0 and x cannot be 1. Now this notation right here, this is your common set notation. So your variable comes first such that all of that. Hopefully that's a little bit familiar to you, but if not, that's the way we write it. All right, let's look at part B. Again, we're doing f of 3, 2. So we're going to say f of 3, 2 equals x value is 3, and the natural log of 2 squared is 4 minus 3. So we have f of 3, 2 equals 3 natural log of 1, which is 0. So nice pretty answer. F of 3, 2 equals 0. And now we're going to find the domain of this function. Now the x out front could be any real number, so that's not a big deal. What we need to look at is we have this natural log here. Remember when you take the natural log is restricted to be greater than 0. So we're going to have y squared minus x is greater than 0 as our domain. And as we mentioned before, the x is any real number. So let's solve this to be y squared is greater than x. So x is less than y squared. I like the y squared on the right. It's just the way it looks. So the domain of this is the set of all xy such that x is less than y squared. I forgot the sketch part, so we're going to go ahead and do this one. The sketch of this, remember that you have your x and y for your domain. So this is just the domain graph. It's not the range. It's just the domain. And we have x is less than y squared. Well, x equals y squared is a parabola here, but it needs to be dotted in order for it to be an inequality. None of our rules for inequality changed. Dotted versus solid, still the same, with its or equal to its solid without its dotted. I'm going to choose a test point of negative 1, 1. When I plug that in, I get negative 1 is less than 1, which is true. So we're going to shade where the test point occurs. And that is the sketch for the domain of that one. So now we're going to come back up and do the sketch of the domain up here. So we have x plus y plus 1 is greater than 0. I'm going to say our domain, I'm going to solve this for y. Y is greater than or equal to negative x minus 1, and x cannot be 1. So we're going to combine those together. And what we have is we have an xy graph. Negative x minus 1 looks like this. It comes down through negative 1, and it is a solid line as I draw it dotted on accident. So here we're at negative 1. It has a slope of negative 1. And when I put in 0, 0, 0 is greater than negative 1, true. So this side is all true, except we do not have this line right here, x equal to 1. It's dotted in here. That line is not included. So that is the sketch of the domain. So we found f of 3, 2, and found and sketched the domain for both. I hope that makes sense. All right, let's look at the next example. So find the domain and range of the function. So since it's in the square root, when we talk about domain, we're going to say 9 minus x squared minus y squared has to be greater than or equal to 0. So let's move those to the other side. 9 is greater than or equal to x squared plus y squared, and rewrite it x squared plus y squared is less than or equal to 9. So if you think about your domain and range as x and y's, what we have is we have a circle with a radius of 3, and it's less than, so it's inside that circle. So that's our domain. The center is 0, 0, and the radius is 3. And that helps us figure out our range. We would say our domain is equal to the set of xy such that x squared plus y squared is less than or equal to 9. Now there's two ways to look at the range. We're going to say that the range then is going to be z such that z equals the square root of 9 minus x squared minus y squared, and x and y are elements of the domain. So as long as you pick values in the domain, when you plug it in, you get the z values. And we would like to be a little more specific about that. This is the beginning of it, but let's think about what this happens. When we do this, z has to be greater than or equal to 0. And if you think about the outside, z has to be less than or equal to 9, based on the fact that we have a circle. Let's be a little more specific here. We could say 9 minus x squared minus y squared. If you have 0, 0 for x, then you get 9 here. So when you take the square root of both sides, you get 9 minus x squared minus y squared is less than or equal to 3. So that means z has to be between 0 and 3, which makes sense. Your z values are going to be between 0 and 3. So we could say that our range then is equal to z such that z is between 0 and 3. It can be written as the interval 0, 3. This example shows the way in which we see this. In regions with severe winter weather, the wind chill index is often used to describe the apparent severity of the cold. This index W is a subjective temperature that depends upon the actual temperature T and the wind speed V. So W is a function of T and V, and we can write W equals the function of T, comma V. Table 1 records values of W compiled by the U.S. National Weather Service and the Meteorological Service of Canada. So you could look at this table and it tells you the wind speed, the actual temperature and the wind speed. So if the actual temperature is -5 and the wind speed is 60, then this means that the wind chill index is -16. So we would say the wind chill index, which is equal to the function of -5, 60 is -16. And this is in Celsius, and this is in kilometers per hour. So we would say -16 degrees Celsius. The way that's interpreted is subjectively, it would feel as cold as a temperature of about -16 degrees with no wind. So we could do another one and say we are in Florida, so this does not apply. But let's say we have -25 with a wind of 15. So we'd say the wind chill index of F of -25, 15 is equal to -35 degrees Celsius. So if the temperature is -25 with the wind chill, with the wind speed of 15 degrees, that's how they come up with the wind chill index. And it's interpreted as it would be like -35 degrees with no wind. So it's an interesting application of what we're looking at. This example shows you about an important result. In 1928, Charles Cobb and Cobb-Douglas published a study in which they modeled the growth of the American economy. So you can see this table here, and you can read through all of this, but they considered a simplified view of the economy in which production output is determined by the amount of labor involved and the amount of capital invested. So you can see here that we have multivariables happening. While there are many other factors affecting the economic performance, their model proved to be remarkably accurate. So there's the function they used, and then you can see the chart over here. And I wanted you to see they used the method of least squares to fit the table to this function. So here they have a function using the algebra that you've learned along the way. And it says if we use the model given, then we can see two results in the years 1910 and 1920. What's interesting is this function has been used in many settings, ranging from individual firms to global economics, and it has been known as the Cobb-Douglas production function. Now, the domain is the set of points L, K, such that L is greater than or equal to 0 and K is greater than or equal to 0, because L and K are labeled in capital and are never negative. So just an interesting result to look at before we move to the next section. The second part of this section is graphs. So another way to visualize the behavior of a function of two variables is to consider its graph. So here we have the definition. If f is a function of two variables with a domain of D, then the graph of f is the set of all points x, y, z in R3, such that z equals f of xy and xy is in D. We kind of looked at that a little bit earlier when we talked about the range, but we're going to look at this a little more. When we take the graph of a function of y equals x, we're looking in 2 space and we have a curve, but here we're looking in 3 space. So we're going to have a surface, and our surface is going to be an equation where z equals f of xy. So the set of all points gets mapped into the surface. So down here you have the domain, and it's not really part of the graph. And when you graph it, you get x, y, and then z, the function in terms of x and y. And that gives you your surface that we're looking at here. You can visualize the graph of the surface as lying directly above or below the domain in the xy plane. So let's look at a couple. All right, so this problem here says to sketch the function of x, the function in terms of x and y, where you have 6 minus 3x minus 2y. So we could rewrite this as z equals the function of xy, 6 minus 3x minus 2y. Now you're not going to waste time on that in the future. We're just going to say z equals 6 minus 3x minus 2y. So let's bring the x and the y over with the z. So we have 3x plus 2y plus z equals 6. And you can see the plane that we worked with in chapter 12. And the easiest way to picture the plane is to look at the intercepts. So the x-intercept would be 0 for x and y, 0 for y and z. I'm sorry about that. So we have x equals 2 when you pick 0 for y and z. The y-intercept, we're going to pick 0 for x and z. We divide to get 3. And the z-intercept, we let 0 be used for x and y, and z equals 6. So then if we're going to sketch this plane, we go back to what we learned in chapter 12, the first chapter in this section. And my x value is going to be 2, my y value is 3, and my z value is 6. So I'm going to connect the plane connecting these, go to my beautiful pencil option here and kind of draw it in so you can see the piece of paper, the plane that hits these intercepts. So that's the sketch of the graph of that function. Now, this example is a special case of the function. Let me write this in. We're going to say f of xy equals ax plus by plus c. And this is called a linear function. And it forms a plane in 3 space, but it kind of has the feel of a linear function. And we can find that since z equals ax plus by plus c, then we can say that ax plus by minus c equals 0 for your form, or you could say equal to c. Either way, this helps you see the plane in our 3 space. It's very similar to the line in 2 space where x plus y plus ax plus by plus c equals 0, or ax plus by equals c are your 2 forms of the line in single variable calculus. So now that we're in multivariable calculus, we see the plane. In this example, we're going to sketch g of xy equals the square root of 9 minus x squared minus y squared. So as before, we're going to let z equal this beautiful equation. I'm not going to reread it. Now, if we square both sides, we get z squared equals 9 minus x squared minus y squared. So we bring everything to the left side. X squared plus y squared plus z squared equals 9. Now you can see that that's a sphere with the radius of 3 and a center at 0, 0, 0. So it's definitely a sphere with center at 0, 0, 0 and the radius of 3. But since we have a square root here, we know that z must be greater than, the square root must be greater than or equal to 0. So z must be greater than or equal to 0. So what we're looking at is we're looking at a sphere, and we're looking at the top half of the sphere. That doesn't go that way. Let's try that again. And so we're going to have 3 on y and 3 on z and 3 on x, and it goes back 3 in every direction as well, but not down. So keep that in mind, and let's look at this one. So I'm going to draw the circle through the xy. I'm going to draw the circle through the top half through the yz, so you can kind of see the sphere taking, the half of the sphere taking place. And the back half is a little dotted to help us know that it's in the back. And we have the top half of the sphere since z is greater than or equal to 0. We can't use one single function of x and y to get the entire sphere, but instead of using g, let's use h. So to get the bottom half of the sphere, we would do the negative part of the square root. So you can see that that would give you the bottom half of the sphere. So the two equations together make up the entire sphere. Okay, so find the domain and range and sketch the graph of h of xy equals 4x squared plus y squared. Now, if you think back to, first let's make this our function in terms of z. So if we say z equals 4x squared plus y squared, then we see the elliptic paraboloid that we saw in chapter 12. If you didn't like it, sorry, it's coming back. If you loved it, great, it's coming back. Either way, so let's talk about the domain and range. The domain, we have x squared and y squared. There's no restrictions on either of that. So the domain is everything in R2. And then the range, if you think about when you square these, your x values are all going to be 0 and higher. Your y values are all going to be 0 and higher. So your range starts at 0 plus 0, which is 0 to infinity. So your domain and range help you figure out the fact that we're sitting in the smallest value for x is going to be 0, the smallest value for y is going to be 0. So we're sitting here, and to this elliptic paraboloid, we're going to go back to what we did in chapter 12. Let's start by letting x equal 0. When that happens, then we have z equals y squared. So we have a parabola in the yz plane. I'm going to draw it light with my pencil. I really like this pencil tool. Now let's let y equal 0. Then this means that we have z equals 4x squared. So it's a skinnier parabola in the xz plane. And then let's let z equals 0. And that means we have 4x squared plus y squared equals some constant k, which is an ellipse, with your major axis at 4 and your minor axis at 1. But what we see is we see elliptical values happening across here. Now, I put a k in there, not on the other ones, but you could say plus some value k. Let me throw that back in. We could say plus k, but it's easier to think of it in terms of the rest. So here we have our elliptic paraboloid happening just like we did before with trace values like we had before. So it works the same as chapter 12. It just now we have we start off with a function in terms of variables. Here you can see a computer generated version of our elliptical paraboloid. And the horizontal traces are ellipses, the vertical traces are parabolas, but we did that. So there's computer generated graphs of several functions. Let's bring that in here. So here you can see them. Notice we get a especially good picture of the function when you rotate it and get views from different vantage points. So You can play with those. It's lots of fun. Then the third part of this section is level curves and contour graphs. So the level curves of a function f of two variables are the curves with equations f of xy equals k, where k is a constant in the range of f. This is going to make more sense in a minute, so just give me a second to get there. But um, it's the points in the domain where f has a certain value k. And an easier way to explain that is it shows where the graph has a height k above or below the xy plane. So it's just you have a constant value k. Now, a collection of level curves is called a contour map. So contour maps are the most descriptive when your level curves are drawn equally spaced values of k, and you assume that's the case unless otherwise. So look at this one. So figure 11 shows you where the contour comes from. In figure 11, you can see the relationship between the level curves and the horizontal traces. And the level curves f of xy equals k are just the traces of the graph in the horizontal plane, and it's really truly just projected down from z to the domain. So if you draw a contour map of a function and you visualize the curves being lifted up, then you can mentally put together a graph. And we see this a lot. We're going to look at very specific examples. So if you look at how this is labeled, f of xy equals 20 here, so it's 20 all the way around. And you can see the numbers being labeled in, and that's the height. So this one has the height of 20, and then it goes up to 35, etc. And this one has the height of 45. So the level curves is the round stuff underneath, and the collection of level curves is a contour map. So when you put all of those red circles together, you have a contour map. So the red one, figure 12, is our contour map, and this is an example of level curves and topographic maps of mountainous regions. So we see this in mountainous regions with GPS and all the maps that we read today. We're used to seeing these contour maps, and I don't know that we think to call them contour maps, but they are contour maps. The temperature function we looked at earlier in the section was a table, but here we have these level curves, and they're called isothermals. So locations that have the same temperature show on the same level curves. So these are isothermals. You can see them happening. It's kind of easy to read, and you're used to that idea. Here in figure 14, we have a map of worldwide precipitation, and there's a key down at the bottom right. You can see the key here. So the level curves are not labeled, but it's separated by colors, and because of the color key, it's done in that way. So it's a little bit different than the graph we looked at before. So a contour map for a function is shown in figure 15 below. We're going to use it to estimate f of 1, 3 and f of 4, 5. So earlier we had an equation and we plugged our values in. Now we're reading the graph similarly to what we've done in single variable calculus. So f of 1, 3, here we have 1, and up here the y value of 3, so they're going to intersect right here. And now that value this is 70, and this is 80, so it's closer to 70. I would say about 72 or 73. So f of 1, 3 is 73. And then we have f of 4, 5. So here's my x value of 4. I'm going to change to green. Here's my x value of 4, my y value of 5, and I'm coming up here to this point. Now here I'm between 50 and 60. It looks like I'm a little closer to 60, so I'm going to go 56. It looks like a little more than half. So it's an estimation. You just do the best you can with it. Sketch the level curves of the function f of xy equals 6 minus 3x minus 2y for the values of k equal to -6, 0, 6, and 12. Now we could say z equals that function, but when we plug the values in for x and y, then we're going to get some constant k. So 6 minus 3x minus 2y. Now let's bring this over. 3x plus 2y minus plus k minus 6 equals 0. Now this is our constant here. That's our z value, but it's our constant as we look at these planes. So this is if you look at this, this is technically a line. I would like to make a note here, 3x plus 2y equals k minus 6. So if we were to solve for y, we would say y equals negative 3 over 2x plus 1/2 times k minus 6, that value there. Now this is a family of lines, and our slope is negative 3 over 2. You can see that happening. Now we're supposed to do 4 specific level curves where k equals these values. If you think about these contour maps, they're two-dimensional. So we're going to start with k equals negative 6. When we have k equals negative 6, this means we have 3x plus 2y minus 12 equals 0. Now, I don't know about you, but I would like to say that y equals negative 3 over 2x. You add the 12 to the other side and divide by 2 to be plus 6. So we have this line running through here. It's got a slope of negative 3 over 2, and it goes through 6. We don't label all that. We just say k equals negative 6. Now let's look at the next one, k equals 0. So we have 3x plus 2y minus 6 equals 0. If I solve for y, I get negative 3 over 2x. Add the 6 to the other side, divide by 2 to be 3. So we're going to have a parallel line because m equals 3/2. This is at 3. Hopefully my line's kind of parallel, so k equals 0 on this line. And this would be at 3. Now we're going to move into k equals 6. So we have 3x plus 2y, and that makes 0 equals 0. So y equals negative 3/2 x plus 0. So it goes through the origin, and it's running parallel to the other. So k equals 6. And then lastly, we have k equals 12. So we have 3x plus 2y plus 6 equals 0. So y equals negative 3/2 x minus 6. That makes minus 3. Notice our parallel lines here for these level curves. So k equals 12. And that's because the graph of f is a plane. 6 minus 3x minus 2y is a plane. So that's why it comes out looking like that. Let's try another one. Okay, so we're supposed to sketch the level curves of the function g of xy equals the square root of 9 minus x squared minus y squared for k equals 0, 1, 2, and 3. Now, we already know this function is a half a sphere, but now we're doing the level curves. So when we look at level curves, we're going to start off the same way and say the square root of 9 minus x squared minus y squared equals k. If we square both sides, because that's the best way to start is get rid of your square root, and then we can rearrange things to say x squared plus y squared equals 9 minus k squared. Pause for a minute, work through that. It's not hard math. I'm sure you can get there. So what we have here is we have a circle. So let's start off with, remember that our contour graph is XY plane. I'm sorry, XY graph. And then let's start with, let's let k equals 0. So when k equals 0, we have x squared plus y squared equals 9. This is a circle centered at 0, 0 with a radius of 3. So we label it k equals 0. When k equals 1, we have x squared plus y squared equals 8, which is 2 square root of 2. But that's not important. That means it's going to be very close to this radius of 3. And this is k equals 1. Let me label this 3. Now when k equals 2, we have x squared plus y squared equals 5, which is the square root of 5 is a little closer to 2. So it spreads in a little more. I'm very off-centered here. So here k equals 2. And then we have, when k equals 3, we have x squared plus y squared equals 0, which is just the point at the center. So we can label that as k equals 3. So that is our level curves for this equation, for this function. And it's our contour map because it's all of them there together, the set of level curves. So sketch some level curves of the function h of xy equals 4x squared plus y squared plus 1. So because we're doing level curves, we're going to say 4x squared plus y squared plus 1 equals k. Then 4x squared plus y squared equals k minus 1. Now this is an ellipse, so we're going to divide by the constant on the right side. So we have 4x squared over k minus 1 plus y squared over k minus 1 equals 1. But you can't have a 4 here, so if we move it down as a 1/4, then it's the same thing. So you can kind of see your ellipse happening at this point. Now, if k is greater than 1, we have a family of ellipses. So we can do a contour map and then get an idea of what the graph looks like. By the way, this line back here tells us we have an elliptic paraboloid like we did before. So as we look at the level curves, we have an ellipse, and the length of this one is 1/2 times the square root of k minus 1, and the length of this axis is the square root of k minus 1. And this one's larger, so it's our major axis and our minor axis. So these ellipses are stretched along the y-axis. So here you can see the level curves that form our contour map. And then we're going to raise them to get an idea of the elliptical paraboloid. And here you can see the elliptical paraboloid. You take the graph of h and you space them up to form your surface. Here are some computer-generated level curves and the corresponding graphs. If you look at the first one, they kind of group together really close to the origin. And the two views of the graph are interesting there. But sometimes the contour graph of level curves is easier to read than the graph. It kind of helps you out with more about what's going on. Functions of 3 or more variables is the last part of this section. And a function of 3 variables is where you have an ordered triple x, y, z. So you're going to take x, y, z in a domain where D is in R3, or we could say D is a subset of R3. And we write it as, we don't just write x, y, z. We say f of x, y, z is in the domain of R3. So going back to that temperature problem, earlier we said let the temperature be f of x, y, but we can put that into the 3 space by saying let the temperature be f of x, y, t, where x is the longitude and y is the latitude and t is the time. So you can see that we move into more variables in that case. Now again, you can find the domain. You can do all the things we've done earlier, but let's start off with domain. So an example says find the domain of f if f of x, y, z. Notice we're moving into our multivariable calculus. That's what calculus 3 is. And we're going to say the natural log of z minus y plus xy sine of z. All right, so when you consider the domain, start off with the fact that we're in 3 space, so that's important to note. And when we look at the natural log of this, we know that z minus y has to be greater than 0, so z has to be greater than y. And this domain is unrestricted. Therefore, our domain equals the set of x, y, z such that, let's define it more specifically. So the domain of x, y, z in R3 such that z is greater than y. So this is called a half space, and it's the set of all points above the plane y equals z. So if you think about the plane y equals z, z has to be greater than y, so we're sitting above that plane. Now, since we're in 3 space, that means we're actually looking at a 4-dimensional graph, so it's very hard to get. So instead of looking at level curves, we're looking at level surfaces. So think about it, we're looking at level surfaces now. So describe the level surfaces of the function f of xyz equals x squared minus y squared minus z squared. So since we're looking at level surfaces instead of level curves, we're going to say k equals x squared minus y minus z squared. So we could solve for y and say y equals x squared minus z squared minus k. This is a family of hyperbolic paraboloids, and we could sketch out these surfaces. It's very hard to do. So here you can see this family of paraboloids, hyperbolic paraboloids. It's a nice picture. Now, this is a function of 3 variables up here, but we could do functions of more variables. We would just say z equals f of x1, x2, x3, dot, 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 xn. In this case, we have n variables, and so it's called an n-tuple, that x1 to xn. So you have that many real variables, and when that happens, we're in the space of Rn. So we have 3 ways of looking at a function in Rn. First of all, we could say that we have a set of n real variables, and we can write it as x1, x2, x3, xn. Secondly, we can say we have the function of a single point variable, x1, x2, x3, xn. And lastly, we can say we have the vector of a single variable, so we have the vector x, which is x1, x2, x3, xn. I hope this lesson makes sense, and I hope you enjoyed it.